When you open a Java file, you see a functional program. A compiler sees nothing but a flat, unstructured block of text. Watch what happens when you initiate a build. The multi-line layout is discarded, collapsing into a continuous stream of ASCII characters. This raw sequence contains no mathematical structure. To the machine, a while loop is indistinguishable from a typo. The compiler's initial objective is to take this inert text, prove that it constitutes a valid Java program, and build a logical hierarchy out of it. Because processors require strict hierarchy to execute instructions, human text must undergo a rigorous mathematical translation called syntax analysis before any code can run. This transformation is impossible to execute in a single leap. Instead, the compiler processes the text through a rigid two-step pipeline. Phase 1 is lexical analysis. Phase 2 is syntactic analysis. This requires two distinct mathematical models, one to identify the vocabulary and another to enforce the structure. Consider a basic Java statement, an integer declaration assigning the sum of variable a and 42. The compiler hands this line to its first internal tool, the lexer, known as the scanner. The lexer acts as an initial filter. It scans the character stream and discards non-essential data, permanently stripping away the spaces, tabs, and comments that humans rely on for readability. This diagram shows the lexer in action. It utilizes regular expressions to evaluate the remaining characters, grouping them into specific semantic categories. By the time it reaches the semicolon, the flat text string is entirely consumed, replaced by a sequence of labeled blocks. These grouped blocks are called tokens. They form the foundational vocabulary of the compiler. Raw characters carry no semantic weight. Tokens, however, represent discrete, actionable units of Java logic. Having the correct vocabulary does not mean you have a functional program. Take a look at this token sequence. The words are valid Java, but the arrangement is broken. An integer keyword followed immediately by an addition operator. If the compiler attempts to process this sequence, it triggers a hard error. The regular expressions used by the lexer are mathematically incapable of enforcing complex structural relationships or order of operations. The lexer only guarantees the words are spelled correctly. It takes the second phase, syntactic analysis, to prove the grammar is sound. Syntactic analysis is executed by a mechanism called the parser. To determine if a sequence of tokens is valid, the parser relies on a strict mathematical framework known as a context-free grammar, or CFG. This diagram shows a context-free grammar rule provided by the Java language specification. It mandates the precise recursive sequence required to declare a variable. This rulebook acts as an uncompromising template. The parser actively feeds the linear stream of tokens against this template, verifying that every single token aligns precisely with a permitted grammatical structure. The CFG ensures human-written code conforms exactly to the mathematical definition of the Java language. Validating the grammar is only half the parser's job. It must generate a machine-readable output structure. The final output of the front-end pipeline is the abstract syntax tree, or AST. Watch this linear sequence restructure. Based on CFG rules, the assignment operator is pushed up into a root node, branching left to the identifier and right to the addition operation. That addition node branches further downward, capturing the specific variables and literals involved. This branching format definitively locks in the order of operations. The machine will evaluate the lowest branches first and work its way up. Looking at this diagram, elements from the original text are missing. The structural punctuation, semicolons and parentheses, are completely discarded. This is why the tree is abstract. Punctuation is no longer necessary because the physical shape of the graph implicitly dictates execution logic. The AST strips away syntactic sugar, leaving only the pure, actionable mathematical hierarchy of the program. That is the parsing process for a single statement. Scaling up to a full file, that small tree becomes a massive, sprawling network, anchored by a single compilation unit root node. Major branches flow down from the root, splitting from class declarations into method declarations, and finally into individual execution blocks. Before any execution can begin, Every valid Java file ever written must form one of these unbroken hierarchical trees in memory. To a programmer, a modern Java application represents overwhelming complexity. To the compiler, it is a perfectly ordered mathematical graph. The front-end pipeline accomplishes its task in 2 rigid steps. Raw character strings are scanned and condensed into verified tokens. Those tokens are then validated against grammatical rules to construct the hierarchical abstract syntax tree. Once the final node is placed in the AST, the syntax analysis phase is officially over. This pristine tree is the exact data structure handed off to the compiler backend. The backend will use this tree to perform semantic analysis, verifying data types and memory allocations before it generates the executable bytecode. The visual here represents the final downstream result of this entire process, the fluid, frictionless execution of perfectly structured logic. A computer cannot infer what a programmer meant to say. The rigorous mathematics of parsing are the only mechanism that guarantees human intent is safely translated for the Java virtual machine.